Right now, in laboratories scattered across every continent, scientists are performing experiments that sound like pure science fiction. They're teleporting information across cities, building computers that exist in multiple states simultaneously, and discovering that the very fabric of reality behaves in ways that make absolutely no sense according to everything we thought we knew. For over a century, physicists assured us that quantum mechanics was weird but understood, strange but settled science. Then something changed. New experiments started producing results that didn't just bend the rules, they shattered them completely. We've discovered particles that communicate instantaneously across any distance, systems that remain connected regardless of how far apart they travel, and phenomena suggesting that reality itself might not exist until we look at it. But here's what keeps physicists awake at night. The implications reach far beyond laboratory curiosities. These discoveries are forcing us to reconsider the nature of consciousness, the structure of space-time, and whether our universe might be just one bubble in an infinite sea of parallel realities. The quantum revolution isn't coming. It's already here. And what it's revealing about the universe is far stranger than anyone imagined. Let's begin. To grasp what quantum mechanics is actually telling us, we need to abandon something most of us take completely for granted: the assumption that objects have definite properties before we measure them. In our everyday world, this seems absurd. A coffee mug sitting on your desk has a location whether you're looking at it or not. A parked car has a specific color, even when nobody's around to see it. These things feel so obvious that questioning them borders on philosophical nonsense. Except at the quantum level, that certainty evaporates completely. Particles don't possess definite positions or velocities until something measures them. Before measurement, they exist in what physicists call a superposition, simultaneously occupying multiple states at once. Not, we just don't know which state it's in. Actually existing in all possible states simultaneously, like a coin spinning in the air that's genuinely both heads and tails until it lands. The mathematics describing this were developed in the 1920s by physicists like Heisenberg, Schrödinger, and Dirac. Their equations worked brilliantly, predicting experimental results with stunning accuracy. But the equations also produced something deeply uncomfortable, a description of reality that made no intuitive sense whatsoever. Einstein famously hated this. He spent decades arguing that quantum mechanics must be incomplete, that there had to be hidden variables determining outcomes in advance, preserving the clockwork predictability he believed the universe required. The pivotal moment came in 1964, when physicist John Bell developed a mathematical test. Bell's theorem showed that if Einstein was right and hidden variables existed, experiments would produce results within certain statistical bounds. If quantum mechanics was right, and particles really did exist in superposition until measured, the results would violate those bounds. For decades, this remained theoretical. Then technology caught up. Starting in the 1970s and accelerating through the decades since, experimenters performed increasingly sophisticated tests. They sent entangled photons in opposite directions, measured their properties, and compared the statistics. Again and again, the results violated Bell's inequalities. The universe was not behaving like a deterministic machine with hidden gears. It was behaving exactly as quantum mechanics predicted, with genuine randomness and instantaneous correlations that seemed to defy the speed of light. These weren't small effects or ambiguous results. The violations were clear, consistent, and impossible to explain with classical physics. Reality, at its most fundamental level, is not made of definite things in definite places. It's made of probabilities, potentials, and possibilities that collapse into actuality only when observed. The implications shake the foundations of everything we think we know about existence. Consider what this means for a single electron. Before you measure its position, it doesn't occupy one location. The mathematics describes it as a wave function spread across space, with different probabilities for finding it at different locations. Measure it, and the wave function collapses. Suddenly, the electron has a definite position. But here's the disturbing part. Nothing in the equations tells us why or how that collapse happens. One moment, you have a spread out wave of probability. The next moment, you have a particle in one spot. The transition between these states remains one of physics' deepest mysteries. This isn't a problem with our knowledge. It's a problem with reality itself. The electron genuinely doesn't have a position before measurement. Asking where it was before you looked is like asking what direction north was before compasses were invented. The question assumes something exists that simply doesn't. Properties like position and momentum come into being through the act of observation. They're not revealed, they're created. Some physicists tried to argue this was merely an epistemological issue, a limit on what we can know rather than a statement about what exists. But subsequent experiments closed that loophole. The most famous involves something called quantum entanglement, a phenomenon Einstein derided as spooky action at a distance, because it seemed to violate his theory that nothing can travel faster than light. Here's how entanglement works. Create two particles in such a way that their quantum states are correlated. Send them flying apart, light years apart if you want. According to quantum mechanics, these particles remain connected. Measure one particle's spin, and you instantly know the other particle's spin, even though that information would need to travel faster than light to get there in time. Einstein believed this proved quantum mechanics was incomplete. There must be hidden instructions each particle carried from the moment of their creation, determining their properties in advance. Bell's theorem and the experiments that followed demolished that explanation. The correlations between entangled particles are too strong to be explained by hidden variables. When you measure one particle, something genuinely changes about the other particle instantly, regardless of distance. Not because information is traveling between them, but because they remain part of a single quantum system even when separated by vast distances. Think about what this means. Separateness, the basic intuition that distant objects are independent things, breaks down at the quantum level. Two particles can be so thoroughly connected that measuring one immediately affects the other, not through any signal passing between them, but because at a fundamental level they're not truly separate entities. The universe doesn't respect our intuitive boundaries between here and there. This gets even stranger when you consider experiments with delayed choice. In these setups, you can decide how to measure a particle after it's already passed through an apparatus, and that future choice affects how the particle behaved in the past. Not appears to have behaved, actually behaved. The distinction between cause and effect, between past and future, becomes fuzzy. Time itself seems less rigid than our everyday experience suggests. One particularly mind-bending version involves what's called the quantum eraser experiment. Send a photon through a double-slit apparatus where it can take two paths. Normally, this creates an interference pattern proving the photon went through both slits simultaneously. But add detectors that record which path the photon took, and the interference pattern vanishes. The act of measurement retroactively determines whether the photon behaved like a wave or a particle. Now here's the twist. Entangle that photon with another particle before it reaches the slits. Later, after the first photon has already hit the detector screen, measure the entangled partner in a way that reveals which path the first photon took. The interference pattern disappears. Measure the partner in a way that erases that information, and the interference pattern reappears. Your choice about how to measure one particle retroactively determines how its entangled partner behaved earlier in time. This isn't science fiction. This is experimental fact, repeated in laboratories worldwide, with consistent results. The universe seems to operate in a way that violates our deepest assumptions about how time flows and how causality works. Future measurements can influence past behavior, not by sending information backward in time, but by determining what was real about that past event in the first place. Faced with these experimental results, physicists have proposed numerous interpretations trying to make sense of it all. The Copenhagen interpretation, dominant for decades, essentially says, shut up and calculate. The mathematics works. Don't ask what's really happening. Just use the equations to predict experimental outcomes and move on. This deeply pragmatic approach produced incredible technological advances, but left fundamental questions unanswered. Other physicists found this unsatisfying. The many worlds interpretation, proposed by Hugh Everett in 1957, takes the mathematics seriously and argues that wave functions never actually collapse. Instead, Every quantum measurement splits reality into multiple branches. When you measure an electron's position, the universe divides into versions where the electron appears at every possible location. All outcomes happen. We just experience one branch, while countless other versions of ourselves experience different outcomes in parallel universes. This sounds like metaphysical extravagance, but it has certain advantages. It explains why quantum mechanics produces probabilistic predictions without requiring mysterious collapse mechanisms. It preserves determinism at the level of the universal wave function even while individual measurements appear random. And crucially, it makes testable predictions that differ slightly from other interpretations, though detecting those differences remains extraordinarily difficult with current technology. Then there's the pilot wave theory, also called Bohmian mechanics, which brings back hidden variables, but in a radically different way. In this view, particles do have definite positions at all times, guided by a quantum potential field that fills space. The wave function is real, physically present, steering particles along specific trajectories. This restores a kind of determinism and eliminates randomness, but at the cost of introducing instantaneous non-local influences that make many physicists uncomfortable. Each interpretation faces challenges. Copenhagen avoids answering what's actually happening. Many worlds multiplies entities beyond necessity, creating an infinite proliferation of unobservable universes. Pilot wave theories require faster-than-light influences that seem to violate relativity's spirit, if not its letter. Decades of debate haven't produced consensus, leaving the fundamental nature of quantum reality genuinely uncertain. What makes this situation particularly fascinating is that it's not just philosophical wool-gathering. Different interpretations suggest different experimental approaches and hint at different underlying physics. Many worlds suggest looking for quantum effects at larger scales. Pilot wave theories motivate searches for tiny deviations from standard quantum predictions. The interpretation you favor shapes what experiments you think are worth performing and what future discoveries might look like. Meanwhile, the practical applications of quantum mechanics have exploded. Quantum cryptography uses entanglement to create communication channels that are fundamentally secure, where any eavesdropping attempt necessarily disturbs the system and reveals itself. Financial institutions and governments are already deploying these technologies to protect sensitive information against both current threats and future quantum computers that might crack traditional encryption. Speaking of quantum computers, they represent perhaps the most dramatic practical consequence of superposition and entanglement. Classical computers store information in bits that are either 0 or 1. Quantum computers use qubits that can exist in superposition, simultaneously 0 and 1, and every combination in between. A system of just 300 qubits could, in principle, exist in more states simultaneously than there are particles in the observable universe. This doesn't make quantum computers universally faster than classical ones. For many tasks, they offer no advantage at all. But for specific problems factoring large numbers, simulating quantum systems, searching unsorted databases, optimizing complex logistics, they promise exponential speedups that would transform entire industries. We're watching the early stages of this transformation now, as companies and research institutions build increasingly powerful quantum processors. The challenges are immense. Quantum states are extraordinarily fragile. Any interaction with the environment causes decoherence, collapsing superpositions, and destroying the very properties that make quantum computers powerful. Researchers must isolate qubits in extreme conditions, temperatures near absolute zero, electromagnetic shielding, vacuum chambers just to maintain coherence for milliseconds. Building systems that remain quantum long enough to perform useful calculations while being controllable enough to execute algorithms represents one of engineering's great frontiers. Yet, progress continues accelerating. In 2019, Google claimed quantum supremacy, demonstrating a calculation their quantum processor completed in 200 seconds that would take the world's most powerful classical supercomputer thousands of years. Skeptics noted the specific problem was designed to favor quantum approaches and lacked practical applications. But the milestone demonstrated that quantum advantage is achievable, not merely theoretical. The race is now on to extend that advantage to useful tasks. Drug discovery could be revolutionized by quantum simulations of molecular interactions too complex for classical computers. Material science could be transformed by the ability to model quantum behaviors in novel compounds. Climate modeling, artificial intelligence, financial optimization, numerous fields await quantum breakthroughs that might arrive within decades rather than centuries. But there's something deeper happening here than technological advancement. Every quantum computer built, every entanglement experiment performed, every test of Bell's inequalities conducted adds to a growing body of evidence that reality is fundamentally different than our intuitions suggest. The universe is not made of solid things in definite places following deterministic laws. It's made of relationships, correlations, and probabilities that solidify into definite outcomes only through observation. This raises profound questions about the role of consciousness in physics. Does observation require a conscious observer, or does any interaction with a measuring device count? Some interpretations suggest consciousness plays a special role, collapsing wave functions and bringing definite reality into existence. Others argue measurement is purely physical, requiring nothing more than irreversible information transfer to the environment. The consciousness question leads down particularly strange paths. If observation creates reality, and consciousness is necessary for observation, then does the universe require observers to exist at all? Some physicists propose participatory universe models where consciousness and cosmos are fundamentally entangled, each necessary for the other's existence. Others consider this anthropocentric nonsense, pointing out that observation in quantum mechanics is just technical jargon for any interaction that establishes correlations, no different in principle from a rock rolling down a hill. These debates matter because they touch on questions philosophy has grappled with for millennia. What is the nature of reality? Do things exist when unobserved? How do mind and matter relate? Quantum mechanics forces these questions out of abstract speculation and into experimental physics, where actual results can constrain possible answers. We're discovering that reality is genuinely strange in ways philosophy anticipated but couldn't confirm. Consider the measurement problem more carefully. Before measurement, quantum systems exist in superposition. After measurement, they occupy definite states. But what counts as measurement? Where's the boundary between quantum weirdness and classical definiteness? You might think it's wherever conscious observation occurs, but experiments show that's too simple. Quantum effects persist in larger and larger systems, extending to molecules, even to carefully prepared objects visible to the naked eye. Researchers have demonstrated quantum superposition in objects containing trillions of atoms. They've shown entanglement in systems large enough and warm enough that classical intuitions scream it shouldn't be possible. The boundary between quantum and classical seems less like a sharp line and more like a fuzzy transition that depends on how well systems are isolated from their environments. Decoherence, the process where quantum superpositions wash out through environmental interaction, explains this transition without requiring special collapse mechanisms or conscious observers. Yet, decoherence doesn't solve the measurement problem completely. It explains why we don't see macroscopic superpositions in everyday life, why cats are either alive or dead rather than both simultaneously. But it doesn't explain why any particular outcome occurs when we measure a quantum system. The wave function still describes multiple possibilities. Decoherence just spreads those possibilities into the environment so rapidly that recovering quantum coherence becomes practically impossible. The question of why we experience one outcome rather than another remains. This is where the interpretations diverge most sharply. Copenhagen says the question is meaningless, outcomes are fundamentally random, and that's just how nature works. Many World says all outcomes occur in different branches, and we simply find ourselves in one branch due to the nature of subjective experience. Pilot wave theories say there's a definite outcome all along, determined by hidden variables we can't access. Each answer satisfies some physicists, while leaving others profoundly unsettled. What makes this particularly relevant now is that quantum effects are scaling up, not just in carefully controlled laboratory experiments, but in biological systems operating at room temperature, in messy, wet, noisy environments where quantum coherence should be impossible. Yet, researchers have found quantum effects in photosynthesis, where plants appear to use quantum superposition to explore multiple energy transfer pathways simultaneously, selecting the most efficient route. With uncanny accuracy, birds may use quantum entanglement in their eyes to sense Earth's magnetic field for navigation. Even our sense of smell might rely on quantum tunneling to distinguish molecules. These discoveries suggest life itself has learned to exploit quantum mechanics over billions of years of evolution. While physicists struggled to keep qubits coherent for microseconds, biological systems apparently solved the problem eons ago, using quantum effects to enhance efficiency in ways we're only beginning to understand. The boundary between quantum and classical isn't just about size or temperature. It's about how systems interact with their environments, and biology has become exquisitely good at managing those interactions. This opens extraordinary possibilities. If quantum effects contribute to biological processes, might they play roles in consciousness itself? Some researchers propose that quantum coherence in brain structures could explain aspects of subjective experience that seem difficult to reconcile with purely classical neural activity. The idea remains controversial, with many neuroscientists arguing consciousness arises from classical computation and neural networks without requiring quantum effects. But the speculation isn't baseless. Microtubules, protein structures inside neurons, display properties that might support quantum processing. Anesthetics that eliminate consciousness also disrupt quantum effects in these structures. Correlation isn't causation, but it's suggestive enough that serious researchers take the possibility seriously, conducting experiments to test whether quantum coherence exists in brain tissue and whether it could influence neural processing. If consciousness does involve quantum effects, the implications stretch in multiple directions. It might explain why subjective experience feels irreducible to physical processes. We're not just classical machines, but quantum systems where observation and reality become fundamentally intertwined. It could provide mechanisms for free will in a deterministic universe, if quantum randomness contributes to decision-making. It might even suggest ways that consciousness could be more fundamental to reality than conventional materialism assumes. These ideas remain speculative, but they're grounded in real quantum phenomena rather than mystical thinking. The universe has already proven far stranger than classical physics suggested. Exploring whether that strangeness extends to consciousness and subjective experience represents a legitimate scientific frontier, even if the territory remains largely uncharted. Meanwhile, quantum mechanics continues revealing surprises about the structure of spacetime itself. Einstein's general relativity describes gravity as curved spacetime, treating space and time as a smooth geometric stage on which events unfold. Quantum mechanics describes reality as fundamentally discrete and probabilistic, with inherent uncertainty and discontinuous quantum jumps. These two pillars of modern physics are spectacularly successful in their respective domains, yet fundamentally incompatible. Reconciling them requires a theory of quantum gravity, and that search has consumed physics for nearly a century without complete success. String theory proposes that fundamental particles are actually tiny vibrating strings, with different vibration modes corresponding to different particles. It naturally incorporates gravity and predicts fascinating possibilities, like extra spatial dimensions curled up too small to detect directly. But string theory faces challenges. It requires dimensions beyond the 4 we experience, typically 10 or 11 total. It produces an enormous landscape of possible vacuum states, perhaps 500 different configurations, making unique predictions difficult. And despite decades of mathematical development, it hasn't yet produced testable predictions that definitively distinguish it from alternatives or confirm its validity. Loop quantum gravity takes a different approach, attempting to quantize spacetime itself. In this framework, space isn't continuous but made of discrete quantum units, tiny loops of gravitational field woven together into a network. At the smallest scales, space would be grainy rather than smooth, with a fundamental minimum size beyond which the concept of distance breaks down entirely. This approach makes striking predictions. Black hole singularities might be replaced by quantum bounces where matter rebounds rather than crushing to infinite density. The Big Bang itself might be a big bounce, with our universe emerging from the collapse of a previous one. These predictions are difficult to test directly because the effects appear only at the Planck scale lengths around 10⁻35 meters, where both quantum and gravitational effects become equally important. Yet, clever indirect tests are possible. Some loop quantum gravity models predict tiny violations of Lorentz invariance, the principle that physics looks the same regardless of your speed or direction at extremely high energies. Astronomers look for these violations by studying gamma rays from distant cosmic explosions, checking whether different energy photons arrive at slightly different times after traveling billions of light years. So far, no violations have been detected, constraining what quantum gravity theories can look like. Other approaches to quantum gravity proliferate. Causal set theory treats spacetime as fundamentally discrete, built from elementary events connected by causal relationships. Asymptotic safety suggests gravity might be quantum mechanically well-behaved at all scales, without requiring strings or loops. Each approach brings different insights and faces different challenges, with no clear winner emerging from theoretical or experimental considerations. What all these approaches share is recognition that our current understanding is incomplete. At some level, possibly the Planck scale, where quantum and gravitational effects converge, our descriptions of reality must change in fundamental ways. Space and time might not be continuous. Causality might not be absolute. The very notion of a definite geometry might dissolve into quantum foam, where space and time fluctuate wildly. Some physicists go further, suggesting space and time aren't fundamental at all, but emergent properties arising from deeper quantum information structures. In this view, space-time is like temperature, real and useful, for describing large-scale behavior, but not present in the fundamental theory. Just as temperature emerges from molecular motion without being a fundamental property of individual molecules, space-time might emerge from quantum entanglement patterns without being fundamental to reality's deepest level. This idea draws support from developments in quantum information theory and holography. The holographic principle, suggested by black hole physics and developed extensively in string theory, proposes that all information contained in a volume of space can be encoded on the boundary of that volume, like a hologram encoding three-dimensional images on two-dimensional film. This suggests that the interior structure of space might be redundant, a projection from boundary information. Taken seriously, holography implies that three-dimensional space, as we experience it, might not be fundamental. The real physics could be happening on a lower dimensional boundary, with our three-dimensional world emerging as a kind of holographic projection. This sounds like metaphysical speculation, but it's grounded in mathematical results, showing that certain quantum field theories in a volume are exactly equivalent to gravitational theories on the boundary. These equivalences, called AD-CFT correspondence, after the particular spacetime geometries involved, have been proven rigorously in specific cases. They show that quantum mechanics and gravity, apparently incompatible frameworks, can be dual descriptions of the same underlying reality. Neither is more fundamental. They're different languages for describing the same physics. This duality suggests a deeper unity underlying the apparent contradictions between quantum mechanics and general relativity. Space, time, and gravity on one side, quantum fields and particles on the other. But fundamentally, they're the same thing viewed from different perspectives, like how a sphere looks like a circle when seen from the right angle. If this is correct, the question isn't how to make quantum mechanics and gravity compatible. They're already compatible because they're the same theory in different disguises. The challenge is finding the fundamental description from which both emerge, the deeper reality that expresses itself as quantum fields in some contexts, and curved spacetime in others. Recent work on quantum entanglement suggests it might provide that deeper foundation. Einstein and Rosen discovered in 1935 that general relativity allows wormholes, bridges, connecting distant regions of spacetime. Maldacena and Susskind later proposed that these Einstein-Rosen bridges are actually quantum entanglement. Wormholes and entanglement, apparently different phenomena from completely different theories, might be the same thing. When particles are entangled, they're connected by a tiny wormhole. The more entanglement, the stronger and longer the wormhole. This ER equals EPR conjecture. As it's known, remains unproven but has inspired extensive research. If correct, it means quantum entanglement isn't just a weird correlation between particles, it's literally the fabric connecting different regions of space. Spacetime itself might be woven from quantum entanglement. When entanglement is destroyed, space becomes disconnected. When entanglement increases, space becomes more connected. The implications are staggering. The smooth spacetime of general relativity could be emergent, stitched together from countless quantum connections between elementary degrees of freedom we haven't identified yet. Space wouldn't be fundamental, entanglement would be. Distance would be derivative, measuring how strongly different parts of the fundamental quantum system are entangled. This connects to the puzzle of black hole information. When matter falls into a black hole, quantum information seems to be destroyed when the black hole eventually evaporates through Hawking radiation. But quantum mechanics insists information can't be destroyed, it must be preserved somehow. This information paradox has troubled physicists for decades. Holography and entanglement offer potential resolutions. If the black hole interior is encoded in entanglement patterns on the horizon, information isn't destroyed, it's scrambled and spread across the horizon in extraordinarily complex ways, then gradually released as the black hole evaporates. The information is preserved, just in a form so thoroughly mixed up that recovering it would be practically impossible, even though it's theoretically present. Recent calculations suggest this picture is correct. The same information describes both the black hole interior and the Hawking radiation, not two separate things, but dual descriptions of one reality. Exactly like the holographic principle suggests, the interior isn't lost. It's encoded in radiation in ways that satisfy quantum mechanics while maintaining consistency with general relativity. These theoretical developments are reshaping how physicists think about reality's fundamental nature. Instead of starting with space and time and building quantum mechanics on that foundation, we might need to start with quantum information and entanglement, letting space and time emerge as derived concepts useful for describing large-scale behavior, but absent from the deepest level of description. This inversion has practical consequences. If spacetime is emergent from entanglement, then disrupting entanglement should affect spacetime geometry. Some researchers propose looking for signatures of this in precision measurements of spacetime near quantum systems. Others suggest quantum simulators, controllable quantum systems designed to mimic other physics, could create simple models of emergent spacetime, letting us study how geometric properties arise from quantum information. The experimental challenges are formidable. Effects of quantum gravity appear most prominently at energy scales trillions of times higher than any particle accelerator can reach. But nature provides high-energy laboratories in neutron stars, black hole mergers, and the cosmic microwave background from the early universe. Each offers potential windows into quantum gravitational physics. Gravitational wave detectors have opened a new observational window. When black holes or neutron stars merge, they create ripples in spacetime that propagate at light speed, carrying information about the collision. Quantum gravity effects might leave subtle imprints on these waves, tiny deviations from general relativity's predictions that could reveal quantum structure in spacetime itself. So far, all detected gravitational waves match Einstein's predictions beautifully. But sensitivities keep improving. Future detectors might reach the precision needed to detect quantum corrections, assuming such corrections exist at observable levels. Even null results would be valuable, constraining what quantum gravity can look like, and eliminating theoretical possibilities that make wrong predictions. The cosmic microwave background offers another testing ground. Quantum fluctuations in the early universe, stretched to cosmic scales by inflation, created density variations that eventually became galaxies. The precise pattern of these fluctuations encodes information about quantum processes operating when the universe was a tiny fraction of a second old, at energy scales approaching where quantum gravity becomes important. Detailed measurements of the microwave background have already constrained inflationary models and tested quantum predictions with exquisite precision. Future experiments with even greater sensitivity might detect signals of quantum gravitational effects imprinted during the earliest moments, offering direct evidence of how quantum mechanics and gravity intertwine. Meanwhile, the implications of quantum mechanics continue rippling through philosophy and culture. The observer effect, where measurement changes what's being measured, resonates with postmodern critiques questioning objective reality. Quantum superposition appears in popular culture as metaphor for ambiguity and multiplicity. Entanglement becomes shorthand for mysterious connections transcending space and time. Some of these cultural appropriations distort the physics badly, using quantum jargon to justify claims having nothing to do with actual quantum mechanics. Quantum healing, quantum consciousness applied indiscriminately. Quantum mysticism, these typically involve misunderstandings or deliberate misrepresentations of quantum phenomena. Real quantum effects require specific conditions typically absent in living systems at human scales. Invoking quantum mechanics doesn't magically explain away difficult questions. Yet the genuine quantum reality is strange enough without embellishment. Particles really do exist in superposition until measured. Entanglement really does create correlations that persist across arbitrary distances. The universe really is fundamentally probabilistic and non-local in ways that defy classical intuition. These facts, established by rigorous experiment and mathematical proof, challenge our basic assumptions about how reality works. This challenge isn't going away. As quantum technologies proliferate, quantum weirdness will become increasingly relevant to everyday life. Quantum encrypted communications will protect sensitive data. Quantum sensors will detect gravitational waves and magnetic fields with unprecedented sensitivity. Quantum computers will solve problems intractable for classical machines. The second quantum revolution, moving from understanding quantum mechanics to exploiting it technologically, is transforming from promise to reality. The first quantum revolution gave us transistors, lasers, and modern electronics. Every computer, smartphone, and LED light relies on quantum mechanics even if users never think about wave functions or Planck's constant. The second quantum revolution is making quantum effects more direct and visible, building technologies that actively manipulate superposition and entanglement rather than merely benefiting passively from quantum behaviors. We're approaching a point where quantum mechanics won't be confined to physics, laboratories, and philosophy seminars. It will be infrastructure, as fundamental to information technology as classical mechanics is to transportation. Future generations may find quantum computers as unremarkable as we find classical ones, may take quantum encrypted communications for granted, may work with quantum sensors without pondering the underlying physics. But the deep questions will remain. What does quantum mechanics really mean? Why does measurement collapse superpositions? How do quantum and classical realities connect? Does consciousness play any role? Is spacetime emergent? These questions have survived a century of investigation, not because physicists are lazy, but because they're genuinely difficult, probing the foundations of existence itself. Different interpretations suggest different answers, each with strengths and weaknesses. As experimental capabilities advance, we gain new ways to test subtle predictions that might distinguish interpretations. Techniques for manipulating larger quantum systems, probing shorter timescales, and detecting weaker effects all offer opportunities to gather evidence bearing on fundamental questions. The possibility exists that quantum mechanics in its current form is incomplete, not because hidden variables exist, but because our mathematical framework needs refinement. Perhaps there's a deeper theory that explains why wave functions collapse, or why particular measurement outcomes occur, or how classical reality emerges from quantum substrate. Such a theory would need to reproduce all of quantum mechanics' successful predictions while resolving conceptual puzzles that current formulations leave unexplained. Alternatively, quantum mechanics might be exactly right and complete, with the puzzlement arising purely from trying to fit it into inappropriate conceptual frameworks inherited from classical physics. Maybe reality genuinely is probabilistic, non-local, and observer-dependent, in ways that will always feel counterintuitive because our brains evolved in a classical world. The challenge wouldn't be fixing quantum mechanics, but adjusting our intuitions to accept what experiments clearly demonstrate. Either way, we're living through a remarkable period. Quantum mechanics has moved from abstract theory to practical technology, while simultaneously pushing deeper into fundamental questions about reality's nature. We're discovering that the universe is both more useful and more mysterious than anyone imagined a century ago when quantum theory was born. The experimental capabilities developed for quantum technologies enabled tests of fundamental physics impossible just decades ago. The theoretical frameworks developed to explain quantum phenomena suggest revolutionary ideas about space, time, and information. Theory and experiment drive each other forward in an accelerating cycle that's reshaping human understanding of existence itself. What makes this particularly exciting is that major questions remain completely open. We don't know which interpretation of quantum mechanics is correct. We don't know how to unify quantum mechanics and general relativity. We don't know whether space and time are fundamental or emergent. We don't know if there's one universe or many. These aren't minor technical details, they're central questions about reality's deep structure. The answers may come from unexpected directions. Perhaps advances in quantum computing will reveal new phenomena pointing toward correct interpretations. Perhaps gravitational wave astronomy will detect quantum gravitational effects. Perhaps studies of quantum biology will uncover principles applicable to fundamental physics. Perhaps someone will propose a theoretical framework so elegant and powerful that it transforms how we think about everything. What seems certain is that quantum mechanics will continue surprising us. It has consistently defied expectations throughout its history, revealing that reality is stranger than our wildest imaginings. As we probe deeper, develop better tools, and ask sharper questions, there's every reason to expect more revelations that challenge our understanding and expand our vision of what's possible. The quantum revolution isn't merely technological. It's conceptual, philosophical, even existential. It forces us to confront the limits of human intuition. When grappling with fundamental reality, it shows that the universe operates according to principles profoundly different from everyday experience. And it demonstrates that asking deep questions about existence can lead to practical advances transforming civilization. We've discovered that particles can be in two places simultaneously, that measurements create the properties they detect, that connections transcend space and time, that reality depends fundamentally on observation. We've built technologies exploiting these bizarre phenomena to accomplish tasks impossible with classical physics, and we're only beginning to glimpse the implications. The universe revealed by quantum mechanics is not the comfortable clockwork mechanism of classical physics, where everything has definite properties and follows deterministic laws. It's a reality where possibilities exist in superposition until observation collapses them to actuality, where distant particles remain entangled in single quantum states, where the act of measurement participates in creating what's measured. This reality challenges everything our ancestors believed about the nature of existence. Yet it's our reality, not a philosophical speculation, but an experimental fact confirmed by countless tests and technological applications. The quantum world isn't some separate realm relevant only to physicists. It's the foundation underlying everything we see and experience. Classical reality emerges from quantum substrate through processes we're still working to understand fully. That emergence, how definite macroscopic reality arises from quantum indeterminacy, remains one of physics' deepest mysteries. We understand pieces of it. Decoherence explains why superpositions wash out in large systems. Entanglement with environment explains why we don't observe everyday objects in multiple states simultaneously. But the complete story connecting quantum mechanics to classical experience remains elusive. This incompleteness isn't failure, it's opportunity. Every unanswered question represents a chance for breakthrough, for discovering something genuinely new about how reality works. The history of quantum mechanics shows that when we take nature seriously and follow where experiments lead, we find truths far richer and stranger than our theories anticipated. So as quantum technologies proliferate and quantum experiments probe ever more fundamental questions, we're not just building better devices or confirming established theories. We're exploring reality's deep structure, discovering principles that govern existence at the most fundamental level accessible to investigation. We're learning what the universe actually is, rather than what we assumed it must be. The quantum revolution that's rewriting reality isn't finished. It's accelerating. New experiments, new technologies, new theoretical insights arrive constantly, each adding pieces to a puzzle we're still assembling. The picture emerging is magnificent and unsettling. A universe where observation and reality intertwine, where separation is illusory, where possibilities and actualities coexist in ways that defy intuition, yet follow rigorous mathematical laws. This is our universe. Quantum, strange, beautiful, and thoroughly, wonderfully real.